We're going to look at linear momentum and collisions. So a key idea, getting back to linear momentum, is that if the net external force equals 0, the change in momentum should equal 0. In other words, if there's no external forces, the momentum won't change. So the first thing we're going to do is look at that a little bit, and then we're going to see how that relates to collisions. Let's imagine an exploding disk that is only exploding in the XY plane, so it has no vertical explosion component. And we've got one chunk that is 90 degrees, one chunk here that makes 120 degrees, and one chunk that makes 150 degrees. And what we're going to imagine is that these pieces explode, radially outwards. So the key idea here is that while there is an internal force, check, there is that, there is no external force. And if we think about what's going on, the initial momentum of this disk before the internal explosion goes on equals 0. So therefore, since there's no external force, the final momentum should also equal 0. Well, let's think about how we're going to deal with this. As this thing explodes, my first piece, this piece, is going to explode, out in this direction. So that's going to make a 45-degree angle. And 2 is going to explode out at half of 120, so 60 degrees, or like negative 60 degrees. So this angle here is negative 60 degrees. And then 3 is going to be 75, half of 150, 75 degrees. So it will explode outwards like so, and this angle there, that angle of 3, is going to equal 90 plus 75, or 165 degrees. Okay, so then if we think about what's going on, and break this down a little bit, this object 1 is going to come off with some velocity, so v1, and this is going to be v2, and we've got v3, and those are their velocities that they're coming out with. And if we look in just the x direction, what we know is that mass 1 v1 cos of 45 plus mass 2 v2 cos of negative 60. And let's make sure that we can see that. Mass 2 v2 cos of negative 60. This needs to equal, well, let's write it actually this way. Plus mass 3 v3 cos of 165. So we're adding up all of the momentum in the x directions. Since there was no initial momentum, this whole thing must equal 0. And similarly in the y direction, we're going to get m1 v1 sine of 45 plus m2 v2 sine of negative 60 plus m3 v3 sine of 165 also must equal 0. So by breaking it down into its x and y components and recognizing that there was no external force, we're able to get some equations that relate their velocities. Now, Notice we only have two equations, and there's three variables, the three variables being v1, v2, and v3. So we would need to know at least one of those velocities in order to solve the system of equations. But this is a way for us to kind of start picturing what's going on with regards to momentum. Okay, now let's start looking at collisions. So let's imagine there's this red ball and it's moving along, and all of a sudden it's going to hit the blue ball. Now, a couple things could happen. One, it could hit the blue ball and they could stick together and then they're going to move together. Let's see if I can make that happen. Yeah. So it hits the blue ball and then they move together. That is called an inelastic collision. An inelastic collision, or completely inelastic collision, is when the objects colliding stick together. The other thing that might happen is that the red thing's moving along, or maybe the blue thing and the red thing are moving along, and they hit, and then they're going to bounce off one another. And then potentially they're both moving, or potentially what could happen is they hit and one stays still and the other bounces off. Lots of things could happen, and we'll investigate that. But when they don't stick together, when they bounce off, and when they perfectly bounce off, we call that an elastic collision. And it is called completely elastic when there's no deformation of the two objects, and when that happens, when it's completely elastic, then kinetic energy is conserved. So kinetic energy is conserved if and only if we've got a completely elastic collision. So we're going to look at these two types of collisions now. Let us imagine a completely inelastic collision. So let's suppose that we've got some bullet here, and this bullet has some initial velocity. So we'll say initial velocity of the bullet, and it has some little mass. And it's going to shoot into this block, and this block has big mass m. And it's going to shoot into the block so that at some point it gets lodged into this block. And let's just suppose that we've got a frictionless surface, so that the block and bullet will then start to move after the bullet comes to rest in the block. And so what I want to know is, what's the final velocity of the block and bullet? Well, this is just a straightforward conservation of momentum problem. What we know is that the initial momentum must equal the final momentum. And the initial momentum was just, because the only thing that was moving was the mass of the bullet times the initial velocity of the bullet. That's the initial momentum. And this is going to equal the final momentum. Well, the final momentum is going to be the block and the bullet moving together. They're stuck together. So it's going to be the final velocity of the block and the bullet is the same because they're going to be together. And their masses would be the little mass of the bullet plus the big mass of the block. So quite simply, we see that the final velocity of the whole system is just the mass of the bullet times the initial mass of the bullet divided by the total mass of the system. This is a very helpful equation that we can use for inelastic collisions. Well, let's think about what's going on with the center of mass, the velocity of the center of mass, and let's relate it back to that bullet block problem. So here's that bullet, and it's about to go into this block, and somewhere in the middle, much closer to the block, would be the center of mass. So let's say it's right there. And as the bullet starts to move, before it hits the block, what's going to happen is that the center of the mass is going to be moving toward the block, because the mass of the block stays the same, the mass of the bullet is moving to the right, so the center of mass is going to move to the right. And then the bullet and the block will be stuck together, and the center of the mass is going to keep moving with them. Let's investigate that a little bit more. So we know that momentum equals mass times the velocity of the center of mass, and we learned that in the last unit. And so for this particular problem with two masses, we could say that m is just m1 plus m2 times v center of mass. So here's our expression right here for momentum. What we also know is that momentum equals our initial momentum of the two objects added together. And we know that, provided that there are no external forces, the change in momentum will be zero. So the momentum will be constant. So we could rewrite this using a little bit of algebra and say that momentum of 1 initially plus the momentum of object 2 initially equals m1 plus m2 v center of mass. Now I'm just substituting this in for momentum. Therefore, we can get an expression for velocity of center of mass, which equals the initial momentum of object 1 plus the initial momentum of object 2 divided by the net mass. And what is very, very important and interesting about this is that we see that the velocity of the center of mass of this system is a constant, because the initial momentums aren't changing, and the mass 1 and mass 2 are not changing. Therefore, the velocity of the center of mass must be a constant. This is a helpful idea. The last example we'll do together is a ballistic pendulum example, and this is a really famous physics idea, or problem rather. So we've got some bullet, and it's being shot into a wooden block, and this wooden block is being suspended by two strings, so it can form a pendulum. And what's going to happen is when the block goes into the wooden system, it's going to swing upwards. So imagine this is going to swing up, and our block is going to reach some new kind of height, where we could call this value right there the change in its height. And given that information, what we want to know is what was the initial velocity of the bullet. So simply by measuring that change in height, can we get that initial velocity of the bullet? Okay, well, there are two steps to this problem. So let's think about after the bullet was lodged in. So we're going to look at the after scenario first. After the bullet was lodged in, what we know is that once the bullet is lodged in, we're going to have a kinetic energy problem where kinetic energy is conserved. So in other words, that bullet system had some initial velocity, so we'd say 1/2 little m plus big M v squared equals little m plus big M. Well, all of that velocity right at this moment when the bullet got lodged in, all of that velocity, and that's that v value we're finding is that v of the block bullet, that's all going to go into potential energy. So that's going to equal little m plus big M g h, where h, I'm shorthanding it for delta h. So we can get an expression then for that v value where v is 2gh square rooted. So therefore we just learned that this value here, the v of the block and bullet moving together, must be the square root of 2gh. Well, now we know the velocity the instant the bullet has lodged into the block. So now we can look at before bullet was lodged. Since we have an inelastic collision, when the bullet goes into the block, there's going to be some loss of kinetic energy. So conservation of kinetic energy won't hold up, but we can use conservation of momentum. So we can say that the momentum initially must equal the momentum final. So initially the only momentum was in the little bullet. So little m v initial, and that v initial is what we're looking for. And eventually all of that momentum gets transferred into the bullet and block system, which is going to swing upwards. So that's going to equal that momentum at the moment when it has this velocity, which we found there. So this equals mass of the bullet plus mass of the block times the velocity of them moving together, which is 2gh. So our last step, now we can find the initial velocity of that bullet, which is just the two masses combined, root 2gh, all over mass of the bullet. And there we have an expression without any knowns. But here's an expression for the initial velocity of the bullet, and all it depends on is the mass of the bullet, the mass of the block, and the height that the block lifted up. All right, so the last thing that we'll do is have you try a problem on your own. So here's the problem that you're going to be trying. What's going on here is that there's a 5 kilogram object moving at 4 meters per second. It's going to collide into a 15 kilogram object at 0 meters per second. Afterwards, these two blocks are going to, since it was a completely inelastic collision, these two blocks are going to be moving together as one system. And what we want to find out is what is the final velocity of this system. Okay? And you can either choose, here are your 4 options, that it's going that speed, this speed, here, or you have no idea. Why don't you click on the answer that you think it is?